Hi, everybody. Welcome back to yet another seminar for VTSS. Today we have Joshua Chan. Thanks, Josh, for joining us, for being part of our initiative. Let me also thank James, who's going to be our panelist for today. The rules of the game are by now known. We're recording this event. The seminar will go for around one hour. We'll try and remind you when you're close to the time. Then we switch the recording off and we have an informal chat. As usual, if you have clarification questions, just unmute yourself and go. This is easier than writing your question on the chat because we might not see it. Let me also remind that as part of VTS, we've put together a workshop for young researchers in time series, so either PhD students or early career, broadly defined. And you will find all the information on the VTSS webpage. There's a section on, I think, events. And I would say that's it. Josh, you may start, and all yours.
Okay, so thank you very much to be here. And thanks, Michaela, for inviting me, and thanks for organizing to put together these events. So I'm delighted to be here to talk about our latest research. And this is joint work with Obi Poon and Dan Zhu. So I've been working on large VARs for the past few years. A lot of my earlier work was on developing shrinkage priors for large VARs, thinking about what sort of stochastic volatility processes or time variation to incorporate into large VAR. So this is kind of the latest addition in this line of research where we look at settings with missing data. So the original paper was, the main focus was on mixed frequency, large VAR. And it's one of those papers that in the review process that it has become a different paper, a complete different paper, and much better, thanks to the referees' comments and the editors' comments. So they made a lot of very good suggestions, and we decided to basically rewrite the whole paper. So now it's instead of just focusing on VAR, and we have a much broader setting that essentially is any conditionally Gaussian state space model would work. And instead of just looking at mixed frequency data, we can handle essentially for all sorts of missing data you encounter. So let's get started. So there's this quite recent, well, maybe not so recent trend that increasingly people are using large data sets. They are compiled from different sources, right? So you can think of that maybe you are interested in forecasting maybe GDP or unemployment or inflation, but you might also want to incorporate, for example, some higher frequency data from financial markets, or maybe you're interested to get some lower frequency, like survey-based data that can come only maybe every half a year, right? So they are from different frequencies, right? So you will need to figure out a way to make it work. So there's this trend. This trend promises more comprehensive analysis, right? You can use more data to maybe sharpen your inference. A lot of this is also motivated by the idea that you want to incorporate more timely information, right? Whenever there's a number that comes up, you want to update your forecast, this idea of nowcasting. But this trend, of course, also brings a few new challenges. The first is that, like I mentioned, is this large data sets coming from different sources. And so typically you have a lot of missing values, right? So one common one is that if you have a different series, some more recently constructed series, you might not have and some older values, right? So you will have missing data at beginning of some sample. You also have this what is called a ragged edge, that some figures, they come out at a lag, and so you would take some more time to get the data. So at the edge of the Excel file, you have a few of these missing cells. One setting we are particularly interested in is this mixed frequency, right? So you combine data of mixed frequency, quarterly, monthly, or weekly, and combine together. And here I have cited two seminal papers. One, both of them are on mixed frequency data. One using a dynamic factor model, the Aruba one with co-authors, and the other one is using a large VAL, Shofada and Song. So we will talk more about these two papers later. So that is one challenge, is that the missing data pattern could be quite complicated. The other challenge is that now you have a lot of data, a lot of variables coming from different sources, and typically you would need to use some sorts of large-scale time series models to extract information from these data sets, right? And typically, well, I guess one of the most popular models in this area would be dynamic factor models, right? Has been used for the past maybe 2 decades or a bit more. And more recently, the last decade, there are more and more works on using large VAL. It's a bit of a latecomer, but large Bayesian VALs also give a lot of promise. It's a very deep literature. You can do a lot of stuff with large VAL. So that's you would need to use some of these large scale models, right? And of course, even with complete data, estimating these models are already quite hard. And increasingly, people also want to add more flexible features, right? In not just a plain vanilla large homoscedastic VAL, for example. So there's a lot of research on add-ins, for example, some sort of time variation, right? Different types of stochastic volatility or time varying parameters, right? To deal with these structural changes. And then due to the pandemic, or maybe even before that, during the last Great Recession, people realize you would have large shocks, right? So you might want to have some sorts of heavier tail distribution than normal, right? So, and then more recently, I think there's a pickup on this a bit. Well, the Stock and Watson, the outlier detection model that was published in 2016, and now people also combine that component into a stochastic volatility model to deal with the COVID outlier. So there are lots of these flexible features, right? And that, of course, it also adds to the estimation, right? The challenge, make it more challenging. So these two challenges, right? One is the complex missing data pattern. The other is that even with complete data, estimating these large-scale models with flexible features are quite difficult. So what we are going to do in this paper is that we try to tackle both of these issues. Essentially, the core of this paper is to develop an efficient sampling scheme to draw all the missing observations or the missing data in one step. So we set up the model. Like I said in the beginning, that we thought, well, we want to do just mixed frequency VAL, but it turns out our setup can actually apply to a much wider setting. So in now the revised version of our paper, we set it up as essentially a Gaussian state space model, conditional on some latent variables, right? So the setup includes a lot of different models that people are already using, right? Some of these nonlinear, non-Gaussian state-based models. Essentially, is that if you can do data augmentation, you augment some latent variables so that given those latent variables, it is in a Gaussian form, it can be nonlinear, then our method can be applied to that setting. And so that would include some of the models I mentioned, for example, a dynamic factor model with stochastic volatility. And the other is mixed frequency VAR with T-error, or stochastic volatility, or any finite mixture of Gaussian. So our setup is quite general. It includes a lot of different types of models. And our setup can also handle many different types of missing data patterns. Essentially, we are going to just partition the data into observed and unobserved. As long as you can do that, and the algorithm would apply. So the key intuition of the approach is actually very simple. Is that because our setup is that is a conditionally Gaussian model. So the Y given all the other stuff is Gaussian, right? And then we can partition the Y into observed and unobserved. And so the joint distribution of Y, because we are looking at conditional Gaussian model, is Gaussian. And due to the property of the Gaussian distribution, right? So the joint distribution is Gaussian, so the conditional distribution of the missing data, given the observed data and all the other variables, they would be also Gaussian. Okay, so that's essentially the key insight of it. But of course, we still need to work out, well, we know it's Gaussian, we still need to work out the conditional mean and the precision matrix, which is the inverse covariance matrix. Turns out that we can do it quite easily. What is nice here is also that the precision matrix has a lot of structure. In particular, it would be sparse. For many common missing data pattern, it is actually a banded matrix, meaning that it's a special sparse matrix in which the non-zero elements are nicely arranged along the main diagonal. And there are some fast algorithms to do stuff with this banded matrix. For example, if you can do a Cholesky factor of this, is very fast. It's essentially linear. The number of operations would be linear in the dimension of the matrix. So anything you might want to do with this band matrix is very fast. So if you exploit this structure, you can sample from the distribution of the missing data very efficiently. So that's essentially the summary of the algorithm. So we would, of course, look at some other details, but that's in a nutshell what the algorithm does. And then in our paper, we also look at how it actually performs in a series of Monte Carlo experiments, right? We compare to a couple of existing algorithms, show that it's computationally more efficient. And our algorithm also scales well to high dimensional setting with a lot of missing data. And we also look at two applications. One is one that we look at using a large VAR mixed frequency, mixing quarterly, monthly, and weekly data to construct weekly GDP, 22 variable VAR. So that works well. So the second application, I don't think I have time to go over it, but it's a dynamic factor model to extract 8 factors from this quite well-known data set, the FlatMD, McCracken, and data set. They have each data set has something like 128, I think, variables, but monthly variables, but a lot of them have missing values, and we just look at the whole data set and impute the missing values and extract factors and try to interpret them. But I will not have time to talk about it today, but if you're interested, please look at the paper. So that's basically the basic setup. So now I would like to go into some of the details. So the first is I would like to talk about the framework. Right, so like I said, it is written as a conditional Gaussian state space model. So as long as you can write your model in this form, right? So Y would be our data, observe and observe, put them together. I have some time varying parameter alpha, right? Has some state equation that governs its evaluation, and I also have some other parameter beta, right? So they are time invariant. So it's pretty general, and each equation can have stochastic volatility or time. But here is anything essentially, right? As long as they are covariance matrix, and each time you have a different covariance matrix, essentially. So this setup is very general, and it includes a few common examples, like popular models. So it will include dynamic factor models, VAR. I have to mention that sometimes, well, in your setup, you can also have some lag values of Y in X or W. What we are going to do next is to rearrange the equation so that we put everything to the left-hand side, and at the end, we don't have any lag values of W and X. But in any case, it includes VAR, it could. And here, the covariance matrix in the measurement equation, you can pick your favorite stochastic volatility, for example, right? So any of these Collier-Sargent, Vermicelli, Carriero, some common stochastic volatility, anything. You just need to specify the stochastic volatility process that would work. In addition, it doesn't have to be stochastic volatility, right? It could be, for example, t-distribution, right? T-distribution, then I would specify this sigma t to be maybe something, a scalar, lambda t times a constant covariance matrix Q, assuming lambda t to have an inverse gamma distribution, and marginally that has a t distribution, right? So that is just another way to say that t has a scale mixture of normal representation, right? So another way to say it is that if you have a model with t error, you can augment some latent variables, then it becomes a conditionally Gaussian state space model. Another type is these outlier components from Stock and Watson, right? And there, this lambda t would not have an inverse gamma, but it has a two-part distribution, has a point mass at 1, and uniform distribution on some value, say 2 to 20, right? So that is the outlier part. Or any combination would work, where you can have the Stock and Watson outlier component with stochastic volatility, like some of the more recent papers, they combine this. So this setup is quite general in terms of the modeling, right? Essentially, is most of the common models people use, but even some of these more recent models that come of the past few years that would fit into this framework. And now we look at the missing data part, right? So like I said, what we are going to do is just to partition this Y factor, n by 1 factor, into 2 subfactors. One have the superscript O, that's the for observation. So those are the values that you actually have in your data set. The other is the missing part, right? This M. And so our setup allows you every period they can have a different number of observed variables or missing variable. So that the number of observed and missing values there has a subscript T, and they have to add up to N, so it's a partition. And we also define a few things. So this N superscript O is just the total numbers of observed values. You just sum up all these lead to N subscript T and O and so on, and then we stack stuff together. And what we want to do is to partition it, right? And one common way now people deal with these latent variables, right, is to treat them as something unknown, right? These missing variables as unknown, and then you either sample it or you impute some values to it, right? And typically it is done using standard Kalman filter and smoothing algorithms. But if you have a large system with a lot of missing values, right? So if you have you want to write your model into mixed frequency setting, into weekly frequency, and if you have monthly variables and quarterly variable, right, then you would have a lot of missing data, right? Because each month you might have 4 or 5 weeks, right? So you only observe essentially maybe 20% of the observations, and all the rest are missing. If you have quarterly, you would be missing even more values, right? Because each quarter you might have 13 to 14 weeks, so you only observe one value every 13 or 14 weeks, essentially. So it's a bit of a challenge when the number of missing observations is large. And other, maybe it's less of a problem, but if you have complex missing data pattern, like some record edge or somehow there's some value missing, you also need to take special care of it. It's a bit more cumbersome if you use a common filter base, because you have the filtering step, and each iteration you need to take care of the dimension of some of the matrices. So it can be done, right, certainly, but it's also a bit more troublesome. Instead of doing the standard approach, what we are going to do is to develop an efficient way to jointly sample all the missing data, this Y superscript M, in one step, right, all of them N in one step, given the observed data and all the other model parameters and latent variables. So there are 2 main advantages. One is that it can be applied to very high dimension settings. Even if you have a lot of missing data, it's quite fast. And it's also quite efficient. I mean, very easy to implement, right? As long as you can partition Y, which I'm going to describe in the next slide. As long as you can partition this Y into observed and missing, then we are all set, essentially. So the way we are going to do is that, well, first we are going to talk about the conditional distribution of Y, the missing data, given the observed data and all the latent variable and model parameters. And then we'll talk about how we can actually generate from this distribution. So let me also mention that in this paper, we are focusing on the missing values, right? So in your MCMC, right, you still need to figure out how you draw from other parameters, right? But of course, that's the beauty of the MCMC, right? It's very modular. And so once you get the missing data and combine with your observed data, now you get back to the situation with complete data, right? And so you can use some of the existing algorithms to estimate all the other parameters, right? It could still be quite difficult, but those problems are more understood, right? There are actually, well, some of my work and many of the audience here also develop algorithms to estimate these sorts of models. So we are going to rely on earlier results. So this paper focuses on the missing data part. So what we are going to do is to derive the conditional distribution, and it consists of 3 steps. It's actually quite simple. That I last semester, when I was actually working out the math, and I had this econometrics 1, which is the first course, PhD level econometrics course. I put part of it into the exam. So I think it should be quite accessible. It's actually quite simple. First year PhD student, if they are good, they would be able to derive this stuff. So anyway, so the first step is to partition this Y into 2 parts, right? One is the observed data, one is the missing data. So we will have some selection matrix. Dimension is Tn by n superscript O, so the number of observed variables, and the same for the missing is just we change this. So both of these matrices are sparse and they have a full column rank. So in particular, because the reason why they have full column rank is that each column there's only one, and all the elements are 0, and different columns, the 1 would be in different rows. And so that's why they have full column rank. So one example is like this, right? If I have a very, very simple setting, only 2 periods, 3 variables, and these 3 observations are missing and the rest are observed, then I just partition my Y factor into this, right? So the selection matrix looks something like this. You can also check they have full column rank. And so the second step is to write the conditional Gaussian model, stack everything together into this form. So I have this G matrix Y factor and just put everything together essentially. And so just staring at this equation, then you already can see that the joint distribution of YO and YM, they are Gaussian, right? Because that's the model assumption. Given enough latent variables, we can write it as a Gaussian model. And so the joint distribution is Gaussian. And so the conditional distribution of YM given YO, that's also going to be Gaussian. And so we just need to figure out the exact form, right? Work out the mean factor and the precision matrix. So maybe let me just, I have half an hour, go through 2 examples just to show how we can do these things. So the first one is a dynamic factor model. It is written in this form that Y is my observed or missing data, is some linear function of some latent factors. The factors have some VALQ structure. And so you can quickly check if I stack everything together, it has this form. I just need to define this matrix H, which is a conical product, essentially just T copies of this factor loading matrix. And so G is equals to S, right, essentially. So this is the easy part. And if you have a VAL with an outlier component, so essentially is I already described, the covariance matrix is just a product of a scalar. This is one type of outlier component. You can also have something a bit more general, but let's go with this. And so Q is time invariant, and this outlier component has 2 parts. You have a point mass as one that denotes the regular observations, and then you can inflate the variance in a way to denote they are the outliers. So this O is has a distribution from 2 to 10. That's the original Stockton-Watson setup. And so if you stack this the system over T and move these lag values of Y to the left-hand side, the VL can be expressed like this. And you have this H matrix. It's some sort of difference matrix, right? And so at the end, it can also be written in the form that we mentioned, that GO and GM in this way, right? And so this also fits our framework.
Sorry, Josh, quick just clarification. So priors are still going to be expressed on B and sigma, correct? You don't need to express it on HB, or it might make no difference.
Say again, sorry.
A prior belief still going to be expressed on the B1, B2, B3.
Yes,
that's it, right? So
yeah, well, so here I am focusing on drawing the missing values, right? So in the step, it would be Y. I would be drawing from the distribution YM given YO and all the other parameters, like B would be conditioned on that.
Okay,
but
okay.
Yeah, another step, you would need to draw the VR coefficients, yes.
B, and then you can always map them into HB. Okay, thanks.
Yes, thank you. So the last step is just to derive the distribution, This turns out to be quite easy to do, right? Because now if you look at the, well, essentially the distribution is jointly Gaussian, and so you just need to work out the conditional distribution of Ym, right? So if you look at the exponents, right, there would be a quadratic form times -1/2, and if you just look at the quadratic form, it looks something like this, right? The quadratic form, right, is like this, and now I just collect terms involving Ym, and so I have a quadratic term, this term times this term, I get this, and there's also a linear term, right? So that comes from this term prime times sigma inverse time the constant term here. So it's like this, and I just give them some names, and I do completing the square essentially. I have a quadratic term, I have a linear term, I just add a constant term so that I can write that in another quadratic term in terms of Ym, right? So now it's the exponent is -1/2 times this quadratic form, and so it is a Gaussian, right? So this would be the precision matrix, and this is the mean vector. So we essentially derive this joint distribution of Y, or the conditional distribution of Ym given Yo. And this that is where the full rank assumption of Gm come in, because I want this to be a non-singular precision matrix, right? But of course, like I mentioned before, basically, as long as you partition the observed and missing factor correctly, then the GM would have a full rank full rank. Okay. So another nice things about this representation is that the precision matrix is actually sparse. Well, I would like to say it's band, but of course our setup is very general, right? So you can come up with some example, some missing value at some a bit odd place, and it is not band. But for most of the examples, we look at mixed frequency, missing data at the beginning or record edge, they would all be band matrix. So it's even better than sparse. And this conditional distribution, even though it's very high dimensional, it can be evaluated very quickly. And so you can also evaluate what might be called the observed data likelihood, right? So you only look at the observed data. So that has this form. Both of them are very high dimensional Gaussian, but with a lot of structure on the precision matrix, so you can evaluate this quantity. So there are a lot of things you can do with it, but what we are going to do next is to sampling from this distribution, right? Because if you have MCMC, that's what we want to do. But there's really nothing much to talk about, because we can just use some of the earlier algorithms to draw from this distribution. Essentially is that if you have a sparse precision matrix, then you can just compute the Cholesky factor of it. And once you have the Cholesky factor of the precision matrix, you can use it to get draws from this distribution. So any of these steps are very fast, because this K precision matrix is a sparse matrix. So you can very easily do all of these computations. And I also want to note that none of these steps you will need to inverse any big matrices. Okay. But if you are interested, we can talk more about this. This comes from some of my earlier work. Okay, so that is the first part. And there are a lot of situations where you might have additional information, right? Here I have two examples. It might be the case that you have some nowcast of GDP. So GDP figure has not been released yet, but you have some very high quality nowcast from, say, professional forecasters, right? And you want to incorporate that and link it to the missing value of the GDP, for example, right? And another setting we are interested in is that mixed frequency setting, that you observe the quarterly GDP and you want to link it to the, say, week-on-week GDP growth, for example, then there would be some linear restrictions restricting the possible values of the missing values of the GDP numbers, essentially. So to tackle this sort of setting, we have this way to do it. So suppose I have another n/1 factor, this C, that is informative about the missing values of Ym, right? So this could be, like I said, some nowcast values, or they could be quarterly GDP growth rates, and you want to link it to the weekly GDP growth, right? And so we consider two types of mapping between C and Ym. The first is what we call the hard constraints. So it's exactly, right? So you want to link the missing value exactly to Z. And this matrix is just specifying the linear restrictions. So one prominent example of these types of hard constraint is, I already mentioned this, some intertemporal constraints for mixed frequency data based on this log linear approximation in this Mariano and Murasawa papers. Very popular. Lots of mixed frequency work use this restrictions or approximation. So that would be one example of this. So here, to be more specific, so suppose I have this Ym, right? I is monthly growth rates of, say, GDP, for example, and every quarter I observe one value, the quarter-over-quarter GDP growth, and I want to link this C to Y, and the log linear approximation would be something like this, right? It's some sorts of weighted average, but not really weighted average because the weights add up to 3, right? If you have quarterly and weekly, they would add up to maybe 13 or 14 weeks. But in any case, you can write this equation into a system that looks like this, right? So that's the first type of constraint, hard constraint. And we also consider soft constraint, right? That because technically these intertemporal constraint, Mariano and Urasawa, they are based on essentially geometric mean approximation of arithmetic mean, essentially. So there's some approximation error. But in practice, people impose hard constraint like this. But maybe more appropriate is to allow for some sorts of approximation error. So we could also consider another case that, well, maybe this is not exactly mapping to Z, but I have some error. So another setting that might fit into this framework is the errors in nowcast, where you have nowcast from professional forecaster, but they are not exactly the GDP value, right? But they are very good, so maybe there's some forecast errors here. And
Josh, we have a question. Somebody cannot unmute, so let me read it. It sounds like Z is part of the observable YO. Isn't that
yes.
true?
No. Well, so depends on how you look at it. So for my setting, right? If I have so say GDP and unemployment, right? So monthly and weekly, quarterly and monthly. Then what I'm going to do, if I have the quarterly GDP figure, I would not put them in YO, I would put them in Z. And so for that example, all the monthly GDP growth rates would be missing. And I want to link the missing part to the observed GDP figures, quarterly GDP figures. So Z would not be in YO. So that's how we set it up. Okay. Thank you for the clarification question. Okay, so that's the second type of constraint, and both of them can be incorporated into the sampling scheme. Incorporated hard constraints turns out to be quite easy. Essentially, is that it's the same Gaussian distribution, but it is going to the jaws you get are going to satisfy this linear restriction. So what that means is that essentially you want to generate a jaw from a degenerate Gaussian distribution, right? And there are efficient ways to do that. Essentially, you just need to adjust it like this. So I would not have time to go over the details, but they are all in the paper. The soft constraints turns out to be even easier because now I can think of the original distribution to be the prior, and the new information is another likelihood. And so it would just involve some Bayesian updating. Now it's just I update my prior, my prior here, given some new information. So I just update the precision matrix and the mean vector. Okay, so that's the methodology part. So next I'm going to talk about some Monte Carlo simulation and maybe the application. So the Monte Carlo study, well, we have more material in the paper, but we will focus on this mixed frequency VAR. That is how we started. So for this exercise, maybe it's useful to think of this quarterly and monthly mixed frequency. This NO, the high frequency variables, you can think of it, they are the monthly variables. I have maybe 10 of these monthly variables and maybe 5 of these quarterly variables. And they are set up like this. And I would sample the whole factor of all the missing values together using our algorithm, the two versions of it, hard constraint and soft constraint. And we also compare with two different common filter-based algorithm. One is essentially Carter and Kohn paper. We use the code provided by Shafada and Song. The other comparison is this Durbin and Koopman algorithm. So we have a lot of different settings, but I will just show you some graph. So maybe here, might be more relevant, is that here I have the number of quarterly variables increasing, right? So it's 5, 10, 15, 20. And as you can see, I have 4 different lines. So this is the computation time in second for tangents. For this is Durbin and Koopman. And here we have a Carter and Kohn, and the hard constraint, the soft constraint. So our algorithm actually scales quite well and also quite competitive compared to existing algorithms. And among the two, the soft constraint is actually faster, more efficient. And different settings, if you increase the time, right, from 200 to 1,000, and the number of lags in the VAR, 12 lags. So they are all performing quite well, especially the soft constraint. So that's actually our preferred algorithm, because even if you want to use the hard constraint, you can approximate it by setting this O to be a very small, well, the diagonal elements to be very small, like 10 to the power -8, for example. And numerically, you would not be able to tell the difference between this soft or hard constraint. And so that might be a way, if you have really large system, that you can impose the soft constraint as an approximation of the hard constraint. But like I said, it might be more reasonable, even if you have a mixed frequency setting, like in those in Mariano and Murasawa, that because they are actually approximations, you might want to consider some sorts of approximation error here in any case. And so that's the simulation. It scales well to high dimension. So the last 10, 15 minutes, I would like to talk a bit about one of our applications. So this is constructing weekly GDP measure. So we would have a large VAR, and we combine data in weekly, monthly, and quarterly frequencies. So altogether 22 variables. We use a common stochastic volatility from this paper on Carriero and co-authors 2016. And this is quite nice, is that there's only one stochastic volatility process. So this H is a scalar, so it scales up the covariance matrix or down, depending on the period. And we actually, in some preliminary work, we also try other stochastic volatility processes, like the Kolesky type SV. Turns out, I suppose, because in our setting, there are lots of missing variables. And that one, you would need to have a very long series to pin down certain stochastic volatility processes. So in the Monte Carlo simulation, it doesn't work very well in our setting. So we, as a compromise, right, it's just too many missing data to pin down the stochastic volatility processes. And so we use this common stochastic volatility. That works quite well in the simulation. So the data, like I said, 22 variables, 16 of them are weekly variable. A lot of these are, some inputs to production, like raw steel production, some retail sales, initial claims for unemployment benefits, some interest rates, and some stock market variables. 5 of them are monthly variable: industry production, CPI, unemployment, non-farm number of non-farm employees, hourly, weekly, average weekly hours, and we have 1 quarterly variable, which is a GDP. So a sample from 2013 to 2022. That's when we started the revision. So this quarterly, monthly, weekly setting is a little bit more complicated. One reason is that the number of weeks in month and quarter might change depending on the month and quarter. And so the intertemporal constraints look something like this now. So this is this N superscript W subscript T is the number of weeks between releases, right? So if you have a monthly variable, then that's the number of weeks in that month. It could be 4 or it could be 5. For quarterly, then it would be something like 13 or 14, depending on the quarter. And so the end results, right? So we have all these missing values, right? So you can have essentially week on week unemployment rates or something like this, right? But one main output that we are interested in is the week on week real GDP. But these are quite volatile because they are week on week. And so we convert these estimates into something more familiar, right? Like mimicking the quarterly growth GDP. So we just kind of using a similar type of intertemporal constraint to convert our estimates. So these are our estimates from the model and just add them up. So we would report this Y sub JT. So we can think of them as quarter on quarter GDP growth. And so this is what we call the aggregate weekly GDP aggregate over the quarter, right? So that's the blue line. Here is the estimate per still mean, and we also have the 68% credible interval. Maybe it's not that visible because of the scale of the graph. But maybe at the end you can see a little bit of uncertainty here. And the cross line are the crosses are the actual observed quarterly GDP growth. So it seems to be working well? Well, I suppose is that this constraint we are imposing, so they must fall on the line. And what we also like is that it kind of track the contraction due at the onset of the pandemic lockdown and the subsequent rebound when the economy opens up. So we also compare our GDP estimate to two conditions index essentially. So one is that this Lewis paper and co-authors, weekly economic index. We are using many of the same weekly variables. The other is this business conditions index constructed by Aruba and co-authors. Both of them are maintained by some regional banks of the Federal Reserve, one in New York and one Philadelphia. So we just download the estimates from the website, and they have weekly estimates, and we convert them back to quarterly numbers. Both of these are based on dynamic factor models. And the comparison is here. So there are three lines, right? Our estimate, the GDP numbers are the blue one, and the pink or red is the business conditions index. The black dotted line is the weekly economic index. So the first thing to note is that our estimate kind of trace the business condition index somewhat similarly. So in particular, it tracks the downturn and the rebound somewhat similarly. But of course, their models is based on dynamic factor models, and they actually construct it so that the average values of factors is 0, and so they kind of fluctuate around 0, whereas our estimates GDP estimates, and over this period from 2013 to 2022, the average GDP growth, annualized quarterly GDP growth is 2%, and so we kind of fluctuate a bit about 0. But overall, they are somewhat similar. Maybe one difference is that our estimate doesn't tell what a bit the downturn is not as steep, and the rebound is a bit sharper. In contrast, the weekly economic index is a little bit different, right? So if you look at the index, that might suggest a bit of not a sharp rebound, right? Pretty. It takes maybe 1 whole year to get back to 0, the value. So one potential driver of this difference is that the weekly economic index, they do not use GDP figures. So it might be the case that this economic index is specific to certain factors that use the steel production a lot or other utilities like electricity, whereas the GDP estimate, our GDP estimate, by the virtue of using GDP, is capturing the whole economy. So that might explain some of these differences. So I'm doing quite well on time. That's good. So I will just wrap up. So this paper, essentially what we do is to propose a different approach to deal with missing data in a time series context, right? And we set it up in such a way that it can be applicable for most of the existing models, right? It's a conditional Gaussian state space model, right? As long as you can augment some latent variables and write your model in a Gaussian form, then our algorithm would apply. And another advantage of our approach is that it's very easy to deal with all sorts of complex missing data pattern, because what you need to do is that before you do any of the estimation, you just need to define the partition matrix, right? So you know what what variables are missing and whatnot. And so you can define them before any for loop. And so once you have those two selection matrices, and you can get all the missing values in one step, essentially. We also show you can tackle some complex missing data pattern and high dimensional models. And in our application, one of them, we use a large mixed frequency VAL to produce weekly GDP estimates. The other application is using the whole FatMD data set with different sorts of missing data and use a different model, dynamic factor model with stochastic volatility. If you are interested, please go ahead and have a look in the paper. Okay, so I would stop here. Thank you very much for your attention. We have the working paper. Well, we only just finished it this week, but this is now on my website. Please have a look if you are interested. Thank you very much.